Okay, this is the module 4 where I will be discussing about the low frequency analysis of a BJT amplifier. Here this slide is explaining you the low frequency response of BJT amplifier. Here we are considering a simple RC circuit which is working as an high pass filter almost. So we are trying to understand the effect of this circuit at the various levels of our system that mostly will be explained in the coming slide. So here RC combination is taken, so wherein we are going to study all the effects of the capacitance along with the resistance that are coming in the system network. So the capacitors that we are considering is the input coupling capacitor CC, bypass capacitor CE, common output capacitor CS, which is also referred as an output coupling capacitor. So the combination along with this resistor, whatever will be the resistive parameters that will be determining the cutoff frequencies. So RC network shown in figure 4.1.1 can be established for each capacitive element and frequency at which the output voltage drops to 0.707 of its maximum value. Once a cutoff frequency due to each capacitor is determined, then we compare all the three cutoff frequencies obtained due to CC, CE and CS, and the one which is at the highest will be deciding our lowest cutoff frequency. The most dominant component that plays an important role is the capacitor CE, because all these three components are adding to the poles, out of which CE decides. CE is the most dominant pole for your frequency response system. Then implementing the analysis of input resistor RC combination to the actual stable amplifier. Here this is our application amplifier, that is we are using a voltage divider common emitter configuration, and this is an RC combination which is present on the input side, CS and RI. So before going to the analysis, perform a DC analysis on this network. So while performing the DC analysis, we have to find the input resistance. So for going to the input resistance, you have to draw an AC equivalent of the given circuit. R1, so this is an input resistance, this is R1. And this is Ri. So when we are considering the effect due to CC, CS, all the other capacitors CE and CC, these are short circuited, so the picture doesn't come over here. So input resistance Ri is equal to R1 parallel R2 parallel beta Re, and mid frequency range the capacitor CS is assumed to be equivalent to a short circuit, and VB is equal to Vi. The resultant in a this results in a high midband gain for the amplifier. that is not affected by the coupling or a bypass capacitor. However, when we lower the applied frequency, the reactance of CS will increase and take an increasing share of the applied voltage signal Vi, neglecting the effect of coupling capacitor and bypass capacitor Ce. For the moment, if the voltage Vb should decrease, it will result in the same decrease in the overall gain for V0 greater than Vi. At higher frequencies, the reactance will be working in this way. Here it is working as a short circuit. At low frequency and at higher frequency, this capacitor is working as an open circuit. So V0 is equal to 0 volts. Here V0 is equal to Vi. At low frequency of an RC circuit between two extremes, the voltage AV is equal to V0 upon Vi, which is shown in this figure. Fine. So the output voltage can be is written as R into Vi upon R plus Xc. This relation represents the magnitude as well as the phase of the quantity, that is output voltage. So it is written over here, V0 is equal to R upon Vi under root of R square plus Xc square. This will calculate the magnitude part. So which is equal to 1 upon under root of 2 times Vi. So if you take the voltage gain, V0 is equal V0 upon Vi, this is 1 upon root 2. So which comes out to be 0.707. This slide will help you in understanding the actual response when Xc is equal to R. What will be the effect of it? When Xc is equal to R, the output will be 70.7% of the input signal, which is shown in this figure. So we take an minus 3 dB gain at when Xc is equal to Xr, or when the reactance of capacitance is equal to the resistance R. This is, and the frequency is going to be 1 upon twice pi RC. So gain is equal to 0 dB under that condition here. When maximum reactance, gain is 0 dB. AV AV is represented as 1 upon 1 minus J times FL by F. So we can distribute this in terms of the magnitude component and phase component, where phase component is tan inverse of FL by F and magnitude is 1 upon under root of 1 plus FL by F whole square. Fine. So the gain AV is equal to 20 log of 1 upon under root of 1 plus FL by F whole square. Magnitude and the phase form is given by these two relations. So overall magnitude comes out to be 20 log of 1 upon under root of FL by F whole square. Ultimately, when you do some assumption that FL by F is greater than 1, that time AV is 20 log of FL by F to the base 10, where lower cutoff frequency is less than the actual design frequency. So we'll try to plot this FL, okay, cutoff frequency. Here this table has been used for plotting this characteristic or the magnitude plot. When FL is equal to F here, that time the gain is 0 dB, that we have already calculated in the previous slides. And when it is half of FL, that time it goes to minus 6 dB. When FL by 4, it is minus 12 dB. and so on. So you plot this particular graph, okay, but this is an ideal graph. If we want to consider an actual graph which is shown by a dotted line, it has to be minus 3 dB, okay, when f is equal to fl under that condition. So this is how we plot our magnitude plot, and the graph on which we are plotting it is called as in similar graph paper, and the plot is represented as a Bode plot. Here we are considering this voltage gain relation. AV is equal to minus 20 log of FL by F to the base 10. Fine. Where F is less than FL. So we get this particular graph. Okay. This slide is explaining you about the voltage gain conversion to dB. So AV is expressed as minus 20 log of V0 upon Vi to the base 10, which is going to express it in dB. Now if I want to express it in numerical form, that is V0 upon Vi, so what we do is, we example you take AV is equal to minus 3 dB. Now from this 3 dB I want to get a numerical value. So AV, take in this particular relation, AV is equal to 10 raised to minus 0.5, so which comes out to be 0.707. Fine, this relation is this conversion is very important in a numerical. If you are given a dB value and you have to express it in numerical, so theta is equal to tan inverse of FL by F. Here it is plotted, okay, in the similar manner. So angle is reducing, phase angle.
Hello. In this video, we are going to try to put some of the low frequency response and high frequency response calculations for transistor amplifiers in context by applying it to an actual amplifier. In this case, a common emitter amplifier. And I haven't entered any values, but we're going to be coming up with expressions for the low frequency response or the low cutoff frequency and the high cutoff frequency. Please note that these are going to be expressions that apply just to this individual circuit. And so the important thing is that you gather the process of how you go about calculating the Thevenin resistances connected to the different capacitors, the actual capacitances, etc. So try not to memorize results because every circuit is going to be a little bit different, but rather understand how we're coming up with these expressions, the process of developing those expressions. Let's get started. So we're going to start with the low frequency response. And you can see before we start that I have drawn a fairly standard common emitter amplifier circuit. Basically a 4-resistor biasing network. I have attached a signal source via coupling capacitor CC1. RS represents the series resistance of the signal source. And then I have a collector resistor RC, an emitter resistor RE, which is bypassed, in this case totally bypassed, by bypass capacitor CBE. And then I'm taking my output out of the collector, since it's a common emitter amplifier, and I'm taking it through a coupling capacitor CC2. And then I have modeled a load connected to my common emitter amplifier, and I've modeled it as a load resistor in parallel with a load capacitor. For the low frequency response, the capacitors that are going to contribute to that response are the coupling capacitors and the bypass capacitors. And so the capacitors that contribute to the low frequency response are going to be CC1, CC2, and CBE in this particular circuit. Each one of those capacitors is going to introduce a pole that's going to generate a high pass type of frequency response, high pass filter. So we're going to calculate the low cutoff frequency due to each one of those capacitors individually. To do that, while I'm calculating the low cutoff frequency due to capacitor CC1, let's say, I'm going to assume that the other capacitors are short circuits so that they don't interfere with my response. Let's go ahead. I'm going to calculate 3 responses then, or 3 cutoff frequencies, the one due to CC1, the one due to CC2, and the one due to CBE. The one due to CC1, they all are going to have, by the way, the same form. It's going to be 1 over 2 pi RC. So this is going to be 1 over 2 pi RC. The trick is in determining what's the right value of R and what's the right value of C. Obviously, the right value of C in this case is going to be CC1 because we are calculating the frequency response due to that capacitor, or the cutoff frequency due to that capacitor. And the R for that capacitor is going to be the Thevenin resistance connected across the terminals of CC1, which I'm going to refer to as R Thevenin 1. Now, what is R Thevenin 1? Well, if we look at the circuit and we look at CC1 and consider the resistors that are connected to it, I'm going to disconnect my signal source, so I'm going to assume it's just shorted to ground. And so I see on one side RS to ground, and on the other side I see R1 to a signal ground, in parallel with R2 to ground, in parallel with beta times little re. I don't know if you can see that. Let me draw it on the side so that it becomes more obvious. So I have CC1, and then I have RS to ground, and then R1 to a signal ground in parallel with R2 to ground, in parallel with the resistance looking into the base of the transistor, which is going to be beta times little re. Notice that I'm assuming CBE is a short because I'm not considering the effect of the capacitor, and so capital RE does not play a role in this particular case. Okay, so this is just beta times little re. These are all going to ground. And so I can see the Thevenin resistance across the terminals of CC1 is RS in series with R1 in parallel with R2 in parallel with beta times little re. So I'm going to write here, our Thevenin 1 will be RS plus the whole parallel combination. All right. And so that will give me the expression for my first cutoff frequency, low cutoff frequency. If I'm calculating the one due to capacitor CC2, is going to have the same generic form, 1 over 2 pi RC. In this case, the C will be CC2, and R will be the Thevenin resistance seeing across the terminals of the coupling capacitor CC2. I'm going to call it R Thevenin 2. Again, I'm going to draw the circuit so it becomes a little bit more obvious, but that's in essence going to be, let's see, we have CC2, and then on one side I have RC to an AC ground, a signal ground, and on the other side I have RL to ground. I'm not going to consider my load capacitance in this case because that's going to play a role in the high frequency response of my circuit, not the low frequency response. So I'm just going to ignore it for now. Assume it's an open circuit. So this will give me R Thevenin 2, which is going to be RC plus RL. And actually, I have not considered the output resistance of the transistor, but I could, and that will just be in parallel with RC. That will be little rho. So I could write, if the case is such that I cannot ignore little rho, I could write it that way. And then finally, we're going to consider the low cutoff frequency due to CBE. It's going to be 1 over 2 pi R Thevenin 3, I'll call it CBE. And R Thevenin 3, as you have probably guessed, is the Thevenin resistance seen across the terminals of capacitor CBE. Oh, CBE, sorry, not 3. And now I'm going to draw that capacitance here, CBE. And we can see that for that capacitor, I will have resistor RE connected in parallel with little re in series with R1 in parallel with R2 in parallel with RS divided by beta. And those are all connected to ground, so I'm gonna join them all together so it's easier to see. So I have capital RE in parallel with the series combination of little re and this overall resistor. Now, how did I come up with that resistor? Well, I need to divide the resistancing from the emitter towards the base by a factor of beta. That's just the inverse reflection rule. And the overall resistance is going to be R1 connected to VCC, which is an AC ground. So it's in parallel with R2, which is connected to ground. And then again, I'm going to assume that all the other coupling capacitors and bypass capacitors in my circuit are shorted because I'm calculating the effect of CBE only. So I'm assuming CC1 is shorted, therefore that gives me another RS resistor, and since in order to do this, calculate the Thevenin resistance, I need to turn off all my sources. I'm turning off my VS source, so that's just a short to ground. And so that's how I come up with the expression of R1 in parallel with R2 in parallel with RS, and then all divided by beta because of the inverse reflection rule. So my R Thevenin 3 will be equal to RE in parallel with series combination of little re plus R1 in parallel with R2 in parallel with RS, all divided by beta. And now I have three values for low cutoff frequencies. The highest one of those values is going to dominate the low frequency response, and so FL is going to be the highest or the maximum value among FL1, FL2, FL3. Okay, let's take a look now at how we will calculate the high frequency response of a common emitter amplifier.